So transition metals tend to form complex ions. We've talked about complex ions, right? What's a complex ion? Complex ion has a central metal ion that has one or more things called ligands that are bonded to it. The ligands are going to be Lewis bases, and they're going to form bonds, coordinate covalent bonds, with that ion in the middle here. So that's a complex ion. When we talk about a coordination compound, that's going to be a neutral compound that has a complex ion and counter ions in order to make it a neutral compound, right? So this is a complex ion of cobalt and ammonia. So that's the complex ion. Overall, it has a 3+ charge. To make the compound, though, we have to have anions that are going to balance this charge. So we could have 3 chloride ions associated with one of these complex ions. Together, that would make a neutral compound. There's 2 types of interactions for the metal ion. The primary valence refers to the oxidation state of that central metal ion, which would be its charge. And then the secondary valence or coordination number is the number of molecules or ions, the number of ligands that are bound directly to the metal. So CONH3,6Cl3, which is what we were looking at right here. This was originally written kind of like hydrates were, but instead of hydrate, it was an ammonia. But that's an old way of writing formulas. So if we look at the primary valence here, that's referring to the oxidation state. So what's the oxidation state on the cobalt ion here? Well, we've got 3 -1 chlorides, right? So that means this complex ion is a +3 charge, right? So this is 3+ without those guys. And then we look at the ligands. The ligands are neutral molecules, they're not ions. And so the charge on the cobalt must be the same as the overall charge, right? So the primary valence here is +3 as an oxidation state of +3. The secondary valence is the number of molecules or ions bound directly to the metal. So what would that be here? 6. There's 6 ammonia molecules bound to the metal. We can also have other compounds that have the same overall chemical formula, right? So we can have CONH3,5Cl. I'm sorry, it's not the same formula, very similar, Cl2. So here we've got 3 chlorines still, but one of them is a ligand. And so here the valence is going to be the same, but the charge on this is the same. Because this is a -1 and those are both -1s. But this chloride is now bound to the cobalt instead of being a free counter ion. And here we've got 4 ammonias and 2 chlorides attached to the cobalt, and just 1 is a counter ion. So the chloride can replace the ammonia. It can act as a counter ion, as it is over here, or as a ligand. These guys are a little crazy. So a complex ion really is a Lewis acid-base adduct. So the ligand has a pair of electrons that it's going to donate to an empty d orbital on the metal. This is called a coordinate covalent bond because one of the bonding species is providing both of the electrons. Usually in a covalent bond, we've got one electron from each atom, and they're sharing them together, and that's the covalent bond. But here, both of the electrons are coming from one. So here, NH3 is a good ligand here because it's got this lone pair. Silver plus has empty 3d orbitals, and so these electrons can go into those orbitals, and we get this acid-base adduct. So the silver ion is accepting the electron pairs, and the ligands are donating the electron pairs. These are some common ligands. Water, ammonia, chloride. You can also have carbon monoxide and cyanide, thiocyanate, oxalate, ethylene diamine. So this one is usually just called N for short, and oxalate is called ox. And then we have ethylene diamine tetraacetate, which is shortened to EDTA. And that's this guy. He's a big, crazy-looking guy. There are others, but these are common ones. So some ligands can only donate one pair of electrons to the central metal atom, like ammonia only has one lone pair of electrons, so it can only donate one. But some of them can donate two or more. So this is a Lewis structure for ethylene diamine. We've got a nitrogen at each end. Each of those nitrogens has a lone pair. So this can actually attach to that central metal ion at each end. And so it can have two attachments. So a monodentate donates one pair, a bidentate donates two pairs of electrons. And oxalate and ethylene diamine can do that. They can donate two pairs. And then you can also have polydentate that can donate more than two. And the one we're going to learn about is ethylene diamine tetraacetate ion. And that can donate 4 ions. So it twists around, and when you look at it over here, you can see how that would be possible, right? You've got these guys over here, and those guys over there, and then you also have these guys in here. So there's different ways that this can attach, form coordinate covalent bonds with the metal ion. So the EDTA is going to wrap itself around. It often donates 4, but it can donate up to 6 electron pairs. So here we have, this is cobalt with 3 ethylene diamines. They're each acting as bidentate ligands. And here is a cobalt with just 1 EDTA ion wrapped around it and binding 4 places. So we have another word for bidentate or polydentate compounds. So a chelate is a complex ion that has bidentate or polydentate, basically ligands that donate more than one. And so the ligands are called the chelating agents. They cause it to become a chelate. Coordination numbers range from 2 to 12. 4 and 6 are most common. You're going to see 2 happening with the 1+ ions. 6 or less for the first row transition elements. Some of them have odd numbers, but those are unusual. The geometries that these make depend on the coordination number, but also on the number of d electrons that are in the metal ion. So here we have an example of a coordination number of 2, where we have a silver atom with an ammonia ligand on each end, and that's going to have a linear shape. Here we've got a coordination number of 4, palladium with 4 chlorides. That's going to make a square planar. Why doesn't it do tetrahedral? Well, that's because there's some electrons in the d orbitals on the palladium. Here's zinc with ammonia, and that'll make a tetrahedral. And then an octahedral would be something like iron with 6 water molecules. So there's another set of rules for naming coordination compounds. The idea here is that you've got a cation and an anion, right? So the first step is you're going to name the ligands, and the neutral ligands, generally their name is just the name of the molecule. These are exceptions that you should be aware of. So instead of saying, hexa water or something, H2O is called aqua, NH3 is called amine, 2 M's, and CO is carbonyl. And then, so you name the neutral ones first, and then you name the anionic ones with the name of the ion plus the ending modified as follows. So if you have something like chloride, Cl minus is chloride. When you name it as a ligand, you change the ide ending to O. So that becomes chloro. The ates, like sulfate, becomes sulfato. The ites, like sulfite, are sulfito. Right? So we've got an ending of O there. We're going to list the names of the ligands in alphabetical order before the metal cation. So we would list amine before chloro, which would come before nitrito, because A before C before N. We use prefixes to tell how many ligands there are if there's more than one of a particular kind. So we use a di for 2, tri for 3, tetra for 4, penta, 5, hexa for 6. So if we see something that's like trichloro, that has 3 chloride ligands. Tetraamine would be 4 ammonia ligands. What if the name of the ligand already has a prefix? Like ethylene diamine has the di in it. Or, So then what we're going to do is we're going to put parentheses around that name, ethylene diamine, and we're going to use a different set of prefixes to identify how many. So this is where we have bis, tris, and tetrachus to indicate the numbers. The prefixes don't affect the order in which you do the ligands. The ligands are in alphabetical order by their names. The prefixes are just stuck on, okay? Then you name the metal. If the complex ion itself is a cation, then we're going to use kind of the normal name of that metal ion, right? So the metal's name followed by the oxidation state in Roman numerals. So in Chem 1A, we learned that CO3 plus would be called cobalt 3 ion. This is platinum 2 ion, copper 1 ion. So the Roman numeral tells us the positive charge on the metal ion. Some of these ions, though, are anions. The complex ion is an anion. So then the name of the thing has to be different. So now we're going to take the ending of the metal name, we're going to drop that off, and we're going to end it with 8. Again, using the oxidation state written in Roman numerals. So CO3 plus as part of a negative complex ion would be called cobaltate 3. This would be platinate 2, cuprate 1. So some of those metals go back to their Latin roots. Copper is Cu because it's cuprum in Latin, right? And I guess cuprate sounds better than copperate or copate. I don't know, but that's what they do. Aren't you glad you don't have to memorize this? You just have to look it up. Then you write the entire name of the complex ion, ligands first, followed by the metal. So here, PTNH3 2Cl4 2 minus. Okay, so amine is the first alphabetically, and there's two of them. So diamine, and the next is chlorine. So 4 tetra chloro. This is a negative ion, so platinum becomes platinate, and then the charge on the platinum, there's 4 minus here and overall 2 minus, so this platinum must be a 2 plus ion. So diamine tetrachloroplatinate 2.
Why?
Do you have a better way to name these things?
Because we didn't put enough letters.
Naming these things is, and we get a lot of complaint from students about nomenclature rules. But things have to have a name, right? And so this is what people have come up with, and if you can come up with anything better, they might listen to you. But this is what they're going with for now, right? Because if we just call this guy Steve, then we have a lot of things to memorize, right? And so there's a pattern in this name, and we can figure out what it is.
Seems like a C.
Yeah,
How about on Gerald?
Gerald. No, maybe this one's Gerald. So this is CONH3 6, 3 plus. These are neutral ligands, so the cobalt is also 3 plus. A positive complex ion with 6 amines. So hexaamine cobalt 3.
Hector.
Hector.
If you really hate your child, you could name him after one of these.
You could. There have been worse names. So
You're not wrong.
these are tables that you may need to refer to as you're doing homework or that take-home exam. So common ligands here, these are anions, these are neutral molecules. And then the metals, these are the ones that have kind of funky names. Well, not all of them, but you'll see the funky named ones in here. Like lead is plumate, because lead is plumum. And we've got ferrate and orate and cuprate and argentate and stannate. Those are the ones where the element symbol comes from its Latin name. So that was naming the complex ion. When you're naming the compound, right, you're going to have the name of the cation first, followed by the name of the anion. And then we also need to be able to write the formulas for these things from the names. So writing the formula for a complex ion, the symbol for the metal goes first, followed by its ligands. Neutral molecules first, and then anions. If we have more than one neutral molecule or more than one anion, the neutrals go first and then the anions. Well, what if we have two different anions? Then we go with alphabetical order. Seriously, I did not make this up. Okay, let's practice. Name the following compounds. This should make, the stuff in 1A seem easy in comparison. Okay, so the complex ion formula is in brackets. And so sulfate here is the counter ion. So if we just want to look at the complex ion first, this is going to have a 2 plus charge. This is ammonia, that has a neutral charge. What about carbon monoxide? Does that have a charge on it? No. So all of these are neutral. So the manganese must have an oxidation state of what? 2 plus. So we've got Mn 2 plus in here, and we've got carbon dioxide, and we've got ammonia. There's 5 of those and 1 of these. There it is. So we're going to list the ligands in alphabetical order. Okay? So This is carbon monoxide, but it's not called that as a ligand. It's called carbonyl. Why? Because. So carbonyl, there's only one of them, so we're not going to use mono. But carbonyl does not actually come first, does it? Thank you for the puzzled look in the back. Let's write these names first. This is carbonyl, and this is amine. See, it's confusing here because the C comes before the N, right? But the names are different. So this actually comes first alphabetically. 5, so penta, amine. There's only one of the carbonyls, and so we're not going to use a mono. Carbonyl. And then that's manganese, 2, and then the name of the counter ion, sulfate. Pentaamine carbonyl manganese 2 sulfate. Nice. Any questions about that one? Let's look at this one. So here we have sodium ions, and then we have the complex ion in brackets. So here we have a negative complex ion. We've got 2 sodiums, those are each +1, and so the complex ion here must have a -2 charge. So this is PT, Cl4, 2-. So what is the oxidation state of the platinum? +3? +4? +2, I'm sorry. Yes, +2. Because we have 4 negatives here, and so if this is +2, then those will add up to be -2. And then we've got chlorides, and there's 4 of those. So the cation gets named first. The cation is sodium. Here, there's only one kind of ligand, so we don't have to worry about order. But that's going to be tetrachloro. And then this is a negative complex ion. So instead of platinum 2, it's platinate 2. Sodium tetrachloroplatinate. Any questions? Yes?
Can you go over why sodium comes first again?
Yeah, why does sodium come first? This is an ionic compound where we have 2 sodium ions, those are the cations, and then we have 1 negative ion, 1 anion. That is a complex ion. And we always name the cation first and then the anion. In this first one, the complex ion was the positive one, and sulfate is the negative one. So it's always positive, negative, positive, negative. And that happens in the formula and in the name. Great question. Anybody else?
Why is it platinum again?
That's a good question. Why is it platinate instead of platinum? Because this is a negative complex ion. So this one was positive. And so then we just use the metal's regular name. Here, you can think of it as following this pattern, like all the nonmetals, when they become ions, they change the ending of their name, right? The metals are positive ions, cations. They don't change their name. They just maybe get some Roman numerals, right? This goes along with this, Mrs. K's chemistry land, where metals are masculine and nonmetals are non-masculine or feminine. And so, I mean, this is like, back in the dark ages. But, so you've got a guy and the girl, they get married, and the woman changes her last name, right? And on the wedding invitations, it's always Mr. and Mrs., right? It's never Mrs. and Mr. Why? Because that's the way it's done, right? So that helps me to remember that it's the guy first, the positive first, and then the negative one. And so here, this is an anion now, and anions always change the ending of their name, right? Chlorine became chloride, right? Oxygen becomes oxide. We've got a polyatomic ion here. It's sulfate. There's a lot of polyatomic ions that end in 8 oxyanions. And so these here, the metals are also going to take an 8 suffix. Yeah, good question. Anybody else?
Do you get charged for the complex ion by just counteracting whatever's attached to it, right?
Yeah, so you're going to find the charge on the complex ion by looking at the counter ions. And I kind of cheated on this first one because there's just so many letters there. But this is the MnCO NH3 and it's paired with 1 sulfate ion. And so this must be 2+ overall. And we need that so that we can figure out the oxidation state of the metal ion. In this one we had, we got the overall charge, and then we had some charged ligands, and so we got to consider all the charged things. Any other questions?